what I'm going to do today is a quick Hardy-Weinberg equilibrium problem. So what does it mean when a population is in Hardy-Weinberg equilibrium? It means that the population is not evolving for a particular gene. So imagine a gene with two alleles, let's say big A, little a, whatever gene we're looking at. It's just a hypothetical example. Well, the frequency for the dominant allele will be p squared plus 2, so that's p squared is the frequency of the dominant alleles. It's the probability of two dominant alleles coming together randomly in a population. For the heterozygotes, the frequency of heterozygous individuals, in other words, individuals with a dominant allele and a recessive allele, will be 2pq. And the frequency of individuals with two copies of the recessive allele is going to be q squared. So we have the frequency of the three different genotypes of individuals in the population, and that should add up to 1. Now, an example of the kind of problem you could get, you might get a question on a test that asks you, is a particular population in Hardy-Weinberg equilibrium? And they would give you the three genotypes, the three possible genotypes of individuals in a population. So you could have an individual who is big A, in other words, homozygous dominant. Let's say there are 300 individuals who are homozygous dominant. You could look at the heterozygotes and say, all right, there's 275 heterozygotes, and we could look at the individuals who are homozygous recessive and say, okay, maybe there's 550 of those individuals. So to know whether or not that population is in Hardy-Weinberg equilibrium, we want to calculate the actual frequency of the alleles that are in this population. So what did we say? The frequency of individuals, the frequency of an allele is the number of alleles we have in that population divided by the total number of alleles in the population. Sorry, let me say that again better. The frequency of the dominant allele, P, is equal to the total number of dominant alleles in the population divided by the total alleles, period, in the population. And for example, here we say that there's 300 individuals who are homozygous dominant. Each of those individuals has two dominant alleles. So to know how many dominant alleles there are in this scenario, we would multiply the number of homozygous dominant individuals by 2. There are also heterozygous individuals who have one copy of the dominant allele. So we would add those individuals, but we don't multiply that by 2 because there's only one dominant allele for each of those individuals. The frequency means we need to take the total number of alleles. So if we total up the number of individuals in this population, we will get 1,125 individuals. Each of those individuals has two alleles for this gene that we're looking at, so it's 2 times 1,125. What does that give us? If you were to work out the math here, P is going to be equal to 0.39. So what is P? P is the frequency of dominant alleles in a particular population, in this hypothetical population that we've set up here. Now, if we wanted to calculate the number of the frequency of recessive alleles in this population, well, there's a very easy way to do that. The easy way to do that is 1 minus 0.39. So if P is equal to 0.39, then Q is the rest of the alleles, right, which is going to be 0.61. You could also do a similar calculation to this one where you do Q equals 2 times the number of homozygous recessive individuals plus 1 times the number of heterozygous individuals divided by 2 times the number of everyone in the population, and you will get the exact same thing, 0.61. If they add up to 1, then you know you've done your work correctly. Now, to determine whether or not this population is in Hardy-Weinberg equilibrium, you need to calculate the frequency or the expected frequency of individuals in this population now that we've calculated these frequencies. So what do we mean by that? You take p squared as representing the number or the frequency of homozygous dominant individuals in the population. So what did we calculate here? We calculated the frequency of the dominant allele. Here we're going to calculate the frequency of individuals we expect to be homozygous dominant if, and only if, the population is in Hardy-Weinberg equilibrium. So that gives us 0.39 squared, which gives us 0.15 as a frequency. How many, or what is the frequency of individuals that we expect to be heterozygous? 2pq. 2 times the number of homozygous, times the frequency of homozygous dominant, times the frequency of the dominant allele, and times the frequency of the recessive allele. This is the frequency of heterozygotes. So 2 times 0.39 times 0.61. This is going to give us 0.48. That's the frequency of heterozygous individuals that we expect to see in the population. Q squared would be the frequency of homozygous recessive individuals in the population. That's going to be 0.61 squared, which is going to give us, I'll write it over here, it's going to give us, maybe I should have done that, 0.37. To recap, what have we done so far? We've calculated the frequency of the dominant allele, which we represent as P. We've calculated the frequency of the recessive allele, which we have here as Q. The work we've done down here, which is a little crowded, I apologize for that, we've calculated the frequency of homozygous dominant individuals, the frequency of heterozygous individuals, and the frequency of homozygous recessive individuals, right? Which has given us 0.15, 0.48, and 0.32. What some students do, don't do this. Don't add these three numbers up, right? Sometimes you guys take these frequencies and you plug it into this equation. You say, oh, it equals to 1, therefore the population is in Hardy-Weinberg equilibrium. No, what we've calculated here is an assumption. It's based on the assumption that the population is in Hardy-Weinberg equilibrium. If we take these numbers now and we multiply them by the actual observed numbers of individuals in that population, so imagine, I won't do each of them, but we're going to take all of this, okay, or we're going to take each of these, I should say, and multiply it by the total number of individuals in the population, so 1,125, and it should give us the expected amount of individuals that we would see in this population, assuming it's in Hardy-Weinberg equilibrium. So 0.15 times 1,125 is going to give you 171 individuals. 0.48 times 1,125 will give you 540 individuals, and 0.32 times 1,125 will give you 416 homozygous recessive individuals in this population. The final step now is to compare these expected numbers, if the population is in Hardy-Weinberg equilibrium, to the observed actual numbers that we get. 2 words about this. 300 different from 171, 275 different from 540, 550 different from 416. If you could see these two numbers, maybe I could circle them to kind of offset them here. They do seem, off the bat, if you were just to look at them, you would say they're different. Now, what if the numbers were a little bit closer? You would probably have to do some statistics to determine whether or not the differences between these two numbers are significantly different enough. If they're significantly different, then we say that the population is not in Hardy-Weinberg equilibrium and therefore it is evolving. If they are not significantly different, then the population is in Hardy-Weinberg equilibrium and it is not evolving. So what kind of statistical test would you use for this? The chi-square test. We won't do that here, but this video kind of gives you an overview of a typical problem that I like to ask in the evolution unit of our course. Thank you.